The matrix form of the Pauli X gate is the Pauli matrix sigma X. The Pauli X gate is also known as the NOT gate, and is typically represented in a quantum circuit by the letter X or a plus sign. When the X gate is applied to the ground state ket 0, it becomes the state ket 1, and when applied to the ground state ket 1, it becomes the state ket 0. When the X gate is applied to any quantum state, it flips the coefficients of the ground state. When you apply the Pauli X gate to a single qubit, it's the quantum equivalent of the NOT gate in classical computing. This flips the quantum state, so the transformation rule is simple: 0 becomes 1, and 1 becomes 0. Using the formula for calculating the unitary transformation matrix of a single qubit, we can obtain the matrix that corresponds to the X gate. Upon observation, it is found that the matrix corresponding to the Pauli X gate satisfies the mirror formula. When the Pauli X gate is applied to a quantum state with a corresponding vector of real numbers, it is equivalent to reflecting the vector about the line corresponding to an angle of theta over 2, which is pi over 4. We have provided the calculation process and results of applying 4 Pauli X gates to 4 quantum states. The circle in the diagram on the right is called a unit circle state machine. From the diagram, we can see that several typical quantum states are symmetric about the line corresponding to pi over 4, according to the geometric interpretation of the Pauli X gate. The results on the left are consistent with this geometric property. Performing the X gate twice in a row or performing the H gate twice in a row will restore the quantum state. However, if 2 X gates and 2 H gates are alternated, the result will be different. As shown in the figure, after alternating operations, the ground state 1 moves to the symmetrical position on the circle after multiple operations. That is, the symmetric position on the x-axis of the Bloch sphere. Through geometric properties, we don't need complicated calculations to know the process and result of multiple gates acting continuously on a quantum state.